so last time I got started looking at this problem, but we didn't start writing any code, and I spent basically the whole time just on the whiteboard, and I ended right at the solution, but I spent a good amount of time going down wrong paths. So I want to start off by restarting, like comprehending the problem, and then explaining the solution I arrived at, and then we can jump right into implementing a solution for this one. So the problem is, actually, we'll jump right in. So a palindromic number reads the same both ways. The largest palindrome made from the product of two-digit numbers is 9009 equals 91 times 99. So what it's saying is, here's our palindrome, and that's as large as it gets when it meets the requirement that there are two-digit numbers, so 91 and 99 multiply together to give us that. If we made it any higher, then it would either not be a palindrome or it would not be a product of two-digit numbers, right? So if you look at like 92 through 99 here, or any of the other things that are higher, like 98 times 98, they would all be larger products, but they wouldn't be palindromes. And if you look at all the palindromes, none of them if you look at the palindromes, none of them are actually things you can write as the product of two-digit numbers. So there's no way to solve it, is the point. Then it asks, find the largest palindrome made from the product of two three-digit numbers. So last time I spent a lot of time trying to think about different ways to think about this. And the way I really wanted to think about it, let me switch over here. The way I really wanted to think about it was as generating palindromes first, because I could pretty easily generate palindromes by making 3 digits. So one decision was, like, we looked at the range of possible values, and if you take two three-digit numbers, it's either a 5-digit result or a 6-digit result. Since we're looking for the largest, we're going to look at all the 6-digit results first, and if we don't actually find any, we'll be quite surprised, but we'll then rewrite our code to do 5 digits. So we're just going to try to solve this. We're taking a slight cheat on the problem and saying, instead of finding the largest palindrome that's either 5 or 6 digits, we'll just try to find the one that's 6 digits, and then we'll make a mental note that we were cheating, and if we don't find a solution, we have to try 5 digits as well. So then, using that simplification, we can use this formula here to generate 6-digit prime numbers. We just take any 3 digits where f is not a prime, and then g and h can be any digits at all, or f is not the number 0, and g and h can be any digits at all. And then we get a palindrome over here, right? That gives us this thing here gives us the right number. Then the question was, could we find two numbers that multiply to that, such that they're both 3-digit numbers? How would we go about doing that? And then I spent all this time trying to think of an algorithm for searching a way of moving the factors around until it worked. And then I abandoned that as I was getting pretty close to the end of that. I came up with an idea. And the idea was, all right, we'll start by picking a number, our palindrome p. It doesn't actually have to be a palindrome for the rest of the algorithm to do what it's supposed to do. But for our case, that's what we're going to be doing, is we're going to be saying basically pick a palindrome. And the cool thing is, since we're picking them, we'll be able to just pick them in descending order very easily, right? So descending order here, if we come, let's see. So descending order here is where we put, you could put 999 here, here, and here, and then these 3 digits won't ever matter, right? The first the 3-digit choices, all here on the high bits, or the high decimal spots, they will dominate. So whatever those 3 are will tell you the descending order. So 999, 998, 997, and so on, right? We can just check these in descending order, and the first one we find is the solution. So then the only thing we need to do is have an algorithm that can test if there is a way to write that number as the product of two 3-digit numbers. I came up with this thing. And what this thing does is it says we start with 2 points. One's the lowest possible value, 100. The one's the highest possible value, 999. And then we check and see if the product we have from those two is too high or too low. And we increment and decrement a and b to either increase or decrease the size. We never decrement A, we never increment B. So A will be increasing, B will be decreasing, and we'll be using that to squeeze in on the product. Now, it might sound like that's how would that actually work. So I have this little description that I gave you last time of why this works. So the idea is here, you can imagine we have like a box, so all the values are laid out in a grid with 100 is down in the left corner here, 999 is up here in the right corner. And along this axis here, we have the variable A moving, and along this axis here, we have the variable B moving. So A starts at 100, the smallest value, and B starts at 999, the highest value. So it's in this corner here, right? And then what we do is we check our point, and when we check the point, if it's too small, what that tells us is that the value, all of these things here are also too small, because this is where B is increasing or decreasing. So if B gets smaller strictly in this direction, then all of these are also too small if this is too small. Similarly, if this were too big, then since A is strictly increasing along this row of the grid, these would all be too big. So we can eliminate entire rows and columns at a time by each check. And then the other thing we can do is say, like, look, A has to stay less than B the whole time, right? So if B is ever less than A and we didn't find a success yet, then we're done. And that's shown here in the square grid thing here by, like, look, all of these points here are literally the flip of these. There's no points in here that didn't also appear up here already, because, like, you know, it's commutative. So if we went through all the way to here and then we started exploring this side of the triangle, well, these are things we've already eliminated everything in the triangle on this side, which means there won't be any answers there. So we can stop as soon as we get to the point where we're crossing from A being less than B to the other way around, right? So our solution somewhere in this upper triangle, we scan around for it. And then I didn't mention this last time, but we can do a few optimizations here. Like, we'll be able to say, like, from the beginning, we don't have to do it one check at a time, because that'll be 1,000 checks, 1,000 multiplies and comparisons for each palindrome, which it's not terrible. It's, like, actually not clear that that's great either, but we can actually do way better, because we can go like, okay, A times B was too small, but by how much was it too small? And then you find out how many increments you can give to A in one go, right? So if it's 2, it'll just take a little bit of arithmetic to figure out that, like, oh, well, add 2 to A in one step, and then it should be greater than, because the math will tell us it's either greater than or equal to now. It will have a thing that, like, the math will be set up in such a way that this will either be the right answer or it'll be too big. So we'll have guarantee that we've skipped over all the points here and found either the ending point or the turning point. And so then if it's not the ending point, we know we turn, and we just calculate how far do we have to go in this direction until we find a turning point, and we just keep calculating how far to go in each direction. So it can devolve into just 1, 1, 1, 1, but usually near the beginning it'll skip through lots of points quite quickly. So that's our algorithm. Hopefully that makes sense. The main idea, just to say it again, there's 2 ways you can look at the idea of the algorithm. One is we have a small value and a large value, and they're kind of pinching towards each other, trying to find the right pair that multiplies to P. The other way to view it is as this grid of possible combinations where we can eliminate, we have it sorted basically, so that whenever we check a point, we're checking a point where we'll either be too great or too little. Will either be greater than or less than our target, and then we'll be able to eliminate entire rows and columns at a time through the grid. So that's what we're going to do. Let's hop in. So first I want to write that thing, and I'm going to write that in a slightly generic way. So let me try to think of what a good name for this is. This is like it's a product. We're looking for a thing that's a product within a particular bound. So I could find this, like, call this like find bounded product, maybe. And then we have min, max, and target, right? So this is the target value we want to be able to get to. So we know things like min times min is got to be less than or equal to target, and that has to be less than or equal to max times max. And then we're also going to say min is less than max. So these are the requirements we're going to have for the function. And then we're going to say the goal is to return a pair. So how do we want to return a pair? We could we could do it a couple different ways. Let me think. So this might be a good opportunity to look at how in assembly we return a value that's bigger than a register. I think that might be a good thing to do now. So since we're trying to practice assembly stuff anyways, let's do that. And what I'm going to do is I'm going to get some help with this because I don't actually know off the top of my head what it is I need to do like ABI wise here to do that. So first let me check here and see if they say a collie that modifies infield with must restore before a scalar return value that fits into 64 bits, including M64, is returned through the racks. Non-scalar types, including floats, doubles, and vector types, are returned in XMM0. The state of unused bits in the value returned in RAX or XMM0 is undefined. User-defined types can be returned by value from global functions and static member functions. To return a user-defined value type by value in RAX, it must have length 1, 2, 4, 8, 16, 32, 64. It must also have no user-defined constructor, destructor, or copy assignment operator. It can have no private, protected, non-static data members, and blah, blah, blah. It can only have, because the definition has changed in the C++, we don't recommend using ispod for this test. Otherwise, the caller must allocate memory for the return value and pass a pointer to it as the first argument. The remaining arguments are then shifted one argument to the right. The same pointer must be returned by the callee in RAX. Okay. Okay, so we're going to try that. We're going to see if we can write some assembly that will return this pair U64 struct. So what we have to do is we assume that this is no longer our first parameter, right? So it says that the first parameter is actually going to be a pointer to the return value. And then the like type here is kind of like a lie that the low level assembly does not agree. The other thing I could do real quick is I could pop over to Godwall and like just get a second sanity test here on this. So let's see. UInt64T. X and Y, and then let's see here, grab one of these, result equals 0, result dot A equals X plus Y, result dot B equals X, X or Y, return result. Can you resolve that? You need to include standard int. There we go. And then let's see, can you use the compiler CL for now? Visual, what's going on here? Why can't I find? Clang, GCC, MSVC, x64. Yeah, let's grab one of these. One without a scary looking version number. How about that? And then this is in debug right now. Let me tell it to do optimizations. So when it has to you put into RAX what's in RCX right here. RDX. So here's our sum. I think these are the first two parameters, if I remember correctly. Or the second and third parameter, I mean, after we shift it, right? Like here's the pointer, and then parameters 1 and 2 are x and y. So x and y have gone into RDX and R8, so it's adding those two together. And then it's putting that into RAX. It's then combining these with an XOR. At RCX, it stores the result of the sum. Then it moves the return pointer into RAX, and then it moves the result of the XOR into the pointer plus 8, and then finally it's returning. And so yeah, that's doing exactly what the ABI for stuff from over here said it would need to do. So there we go. Let's write this thing. Proc and P. Okay. So let me take the notes here. We have RCX is going to be the return pointer. RDX will be min. R8 will be max. R9, right? Yep. R9 will be target. All right. So at the end, it's going to need to have RAX take the pointer in. Now, in the meantime, what we want to do is figure out how to compute this, like run this algorithm. We're going to throw in our assumptions here. I'm going to use the same layout that I've already been using. Assumptions, so here we have RDX needs to be less than R8. That's this one. RDX squared is less than or equal to the target is less than or equal to the max squared. Okay. Bounded factors, target product. Okay. So now we can do yes, I don't think we actually need to worry about remembering min and max after we get started. So at each step of the loop, what we're going to do is we're going to take, well, that's not quite true. Let me start by thinking about the very first step is a little different than the other steps of the loop, but maybe I could write this the easy way first and get it working, and yeah, let's do it that way. So first I need another register that can contain the product. Where are my volatile registers? So R10 and 11 are free. Okay. I'm going to move into R10, the min value. I'm going to multiply in R10 the max value. I'm going to compare R10 to the target value. Now, if those are equal, then Let's see. Trying to think how I want to lay everything out, but let's just start with. I haven't quite got a plan for how returning. Okay, first I'm going to just have this give a built-in clear result to 0. So it's going to be like this: RCX 0, RCX plus 8 0. Okay. R10 equals RDX times R8. Okay, now if R10 equals R9, go to return min max. If R10 is less than R9, go to too small. Otherwise, we're going to go to too big. Okay. So let's see, if it's return min max, then what we want to do is say move into RCX from the small side is RDX and then the big side is R8. Okay, then we want to write a too small case and a too big case. So when we find that our product is too small, so what we're seeing is A times B is less than P, the target. Then we want to increment RDX. And yeah, what we'll do is we'll have this be loop 0. We'll have go to test. This will be dec R8. And then here we'll have test, which will go like this. Compare RDX to R8. If RDX is greater than R8, then jump straight to return, otherwise jump to loop 0, right? So what we're saying here is we look at RDX and R8 again. We've just interdect them and we compare them, and if they've crossed if boundaries have crossed, so R8 has gotten too small or RDX has gotten too big, then we will jump here and return with all zeros here. So the user of this thing will have to test to see if A is 0. If A is 0, then they didn't get a real result. But in theory, that should just implement the correct thing. If I have done everything correctly. I suppose I probably can't use test since that's an instruction name. And that's a typo. All right, So let's just start with pair U64, find bounded factors, find from 10 to 99, 909. So that's the example they gave us, right? Between 10 and 99, they found that 9009 could be written as 91 times 99. Now we don't really care how it gets written, we just want to see if it finds it. And then what we'll do is we'll write out the pair that it finds. And it worked. Awesome. Now, as I said, there is an issue. So it started off with 10, and it probably it went through 81 cycles of this loop to figure out that the answer was 91, but it probably didn't have to do that. So what we want to do now is upgrade the too small and the too big parts. So if it's too big, we don't just, or too small, we don't just need to increment RDX. What we really want to do is figure out some way to set RDX so that increase RDX so that RDX times R8 is greater than or equal to the target R9, right? So in order to do that, what we need to do is really set RDX equal to the ceiling of R9 divided by R8, right? Or another way I could put it is, if we weren't dealing with just integers, but this was just full-on real numbers for a minute, it would just be this, right? Then in order to make this true, I just have to set RDX like this. But I want to actually have like this restraint, which is that we found the spot where if RDX was one less, it would still be too small, but where it's at, it's either perfect or too big, right? So we don't want to just arbitrarily increase RDX way past the target. We want to increase it only up to this point. So we're looking for the spot where RDX is greater than or equal to this, and where RDX is less than this. So if I rearrange this real quick, we get R9, R8 is less than or equal to RDX is less than R9 over R8 plus 1. So what it's saying is, since this now I have to pick an integer for RDX, and I have a range here that includes an entire unit, right? So this here is like math, real numbers. So this here got turned into this by divide by R8. This here got turned into this by divide by R8 and then adding over the 1. Then I flipped this around and I got this part, and then this part got put together. So I've now bounded this on both sides, where on this side I have this ratio here. And if that's an integer, then that'll be the value I want to pick. But if that's too small, RDX has to be an integer, but I can then go as far up as I need to. If this is not an integer, then this also won't be, but there will be an integer in between them, and that's the value of RDX. So what we want is that the new RDX value is the ceiling of R9 over R8, right? We want, if this is already an integer, we take it, but if this is less than an integer, we round up to an integer, right? And what we don't want to do is accidentally do this, where we do floor plus 1, because then it would be like moving the equal sign over here, and that's not what we want. Okay, so how are we going to do a ceiling on the division here, right? Well, I think it's actually not going to be too hard. This can be written as the floor of R9 plus R8 minus 1 over R8, right? I'm pretty sure that's true. So if you want to take, suppose if R8 is 1, then this just gives you the same thing always. If R8 is 2, then we're adding 1 to it. So if it's already an integer, yeah, Yeah, this works. So what we're going to do is fill that stuff in. So the idea is, first of all, let's compute R9. Let's actually, what we'll do is we'll say R10 equals R9 plus R8. Actually, this needs to be RAX. Unfortunately, we're using RDX as the min variable, but that's not great. So let's recast the role of RDX. We should do this one step at a time. So I'm already using 10 as my filler. So I'm going to have to use R11. The reason I want to do that is so that I don't have to worry about it. When I go to do a divide, I have to use the RAX and RDX registers. So you have to do like this, and I don't want to trample over the min that I need. But I do want to do the divide. I'm just thinking I also could probably do something smart here to avoid the divide once there'll be a point in the algorithm. Well, we're not really measuring it, so I guess like getting crazy about the micro optimization just doesn't make a whole lot of sense, but there is kind of a lot we could do to make this go faster and faster. But anyway, for now, let's focus on this. So let's move into RAX the R9, add into RAX the R8, deck the RAX. So there we go, we've got that, and then we move into the RDX. Well, we can clear the RDX to 0. And then what we're going to do is do RDX, RAX divided by R8. Now, RAX equals the floor of RDX, RAX over R8. And RDX equals RDX, RAX modulo R8. And we set it up so that this here would be all we need, right? We do this work here. You know, what's kind of interesting is there's another way you could do this. Why don't we do something different? Let's not do this. Let's say this is just going to be, yeah, this is just going to be different. So we're going to set RAX to R9 and RDX to 0 and stop right there. Then we'll do the divide. So that saves us doing the add and the decrement. We clear those, we do the divide here. And now this thing here contains a remainder. If that remainder is 0, we're done. We could do a conditional move so that if you get out of here. Where is my, here it is. We have CMOV CC, there we go. So what a conditional move should let me do is only execute the move if a condition is met. So I can do CMOV Z if this is 0, if this is not 0 actually. So if this has a remainder of something other than 0, but it's not CMOV that I need to do, it's an increment. Yeah, Yeah, that doesn't necessarily seem better, does it? I can certainly... I can certainly do this, but I'm not sure that there's any reason to think this is better. In fact, it seems maybe slightly worse. So we'll do it this way. Add that in, subtract one of those, clear RDX, do the divide. Now we can ignore RDX, and the thing we actually need is in here. Put this note back in over here. All right, so there's our divide. That fills this with this. And that's the new value for R11, right? So then we say move into R11 the result that's currently in RAX. We jump to test 0. That still gives the correct result. So that is how we do it on the too small side. We're going to do the same idea on the too big side. Decrease R8 so that R11 times R8 is less than or equal to R9, and R11 times R8 plus 1 is greater than R9. So again, we're shooting R8 down as far as we can to get it into the range where this is true. But now let's rearrange these things to find out what how the range is actually laid out. So we are caring about R8 being less than or equal to R9 over R11, and R8 being greater than R9 over R11 minus 1. That, if I rearrange this side, becomes this. Wait, first we have this is strictly less than R8, which is less than or equal to R9 over R11. Okay, so here what we're seeing is if this is already an integer, we want to keep it. But if it's yeah. So I think this is just a simple, we don't have to do this fancy thing to do around like a ceiling divide. We want a floor divide here. And the reason for that is if R8, or if R9 over R11 is an integer already, then that's the one we want. If not, then there's a range that goes below that integer, the value of R9 over R11, where an integer must be contained. So either way, whatever this is, we want to take it or something less than it, but not more than, but not so much less that it becomes one whole value less, one whole unit less, right? So this just becomes R8 gets the value floor R9 over R11. So R9 goes into RAX, 0 goes into RDX, R9 R9 gets the floor of RDX over RAX, and we go to the test. That part is free. Okay. What happens if I throw in like any other thing here? That didn't halt. So let's take a minute and like test this out. It looks like it might not be fully correct right now. Why is it that I can't see? There it is. There's a program. Okay. You go away. So there's our compare. We get all these flags. They're not equal. Carry flag, sign flag, and with that we can go, are they equal? No. Is it too small? So we have, just to be clear here, we have R11 is our min, R8 is our max, and R9 is our target. And R11 times R8 is too small. So we go to too small, and we set RAX to there. We add in R8 and subtract 1. So now RAX equals R9, the target, plus R8 minus 1. Yep, that seems right. We clear RDX to 0, and then we do the divide. RAX becomes 11. And what it's saying is that's the new value of R11. We jump to the test, compare R11 with R8. 11 times 99 is fine, so we're not broken yet. We jump to the top of the loop, and then we do multiply these into R10. Compare. And let's see, R10 is our product. So R10 right now is this. Yeah, okay. So R10 is 1089. It's too big this time. We jumped to too big. And we knew we would jump to too big because after, yes, that's the interesting part. So now that we have these, we will later be able to skip the part where we do the full intro loop test, and the loop will instead become just testing if we're jumping out or jumping to the other case, right? So we'll have this to get us started, and then we'll have, instead of jump to loop test 0, we'll have a separate test and a separate, right, basically two separate loops that we, or cases that we jump back and forth between. RDX. All right, we divide R8 out. That's supposed to be dividing R11 out, right? Yeah. So that's gonna set this to low. So we get to this point, same thing as before, but now RAX will be, okay, it's 91. That becomes the new value of R9. R9? That's not right. That should be the new value of R8. We're changing the target. There's the bug. R8. So 91 goes there. We compare 11 to 91. It's fine. So we go back up here. We do the multiply. It should be either correct or too small. It's, let's see, it's correct. And so now we return our result and answer, we should be able to evaluate, is 11 times 91. Great. Okay. So we're good, but I wanted to just take one extra step, which is right now we're going through and doing all this extra multiplying up here. And we really only need to do that when we get started, because here we'll do the multiply to figure out which way we go. And then after that, I mean, we still have to do the multiply, I suppose, but what we really could do, so there is a reason why it would be cool if we were using remainders here, because if the remainder is 0, that tells us we found our result. Oh, yeah. This gets pretty interesting. We could use the result of the divide. Well, let's just do this with extra multiplies for now, and we can make more progress later. But the thing we can do is, I guess, like one less test. Yeah, we'll push it a little farther than that. But for now, what we're going to do is say, instead of jumping to test 0, the too small case is going to go if R11 is greater than or equal greater than R8, go to return. That's this stuff here. Otherwise, do this. And the new part here is what used to happen in loop 0. So we'll have do the multiply. Yeah, we could definitely get rid of the multiply. That would be the best part. Basically, we're doing this part separately, except now we know we're not going to go to too small. We're either going to be done or we'll go to too big. And so what we can do is, instead of having to do this multiply and then this compare here, we'll be able to rely on just whatever's sitting around in RDX after this divide to tell us where to jump. That's the plan. Because if that, what we'll do is we'll be able to look at the remainder and go, ah, the remainder indicates that the division worked out cleanly, and there was, so when we multiply, we'll get back exactly the target, right? Basically, like, the remainder will tell us whether or not this here is an equality. And if it is, then we go to done, otherwise we go to too big, and we never have to do a multiply. All right, so that's the too small version, the too big version. So we do the divide here, check if we need to go to return, do the multiply, and then here, but we just jump to too small if they're not equal. Good. Good. All right. So now let's see if we can do the idea of eliminating the multiply. So to do this, what we're going to do is say, forget this again. We're going to go with the fancy idea. Do our divide cleanly and move the result into R11. Then what we're going to do is we're going to say, check our R11 might not be right. It might be too small. So when we want to take this here, it might have rounded down and we wanted to round up. So we'll look at the remainder. If the remainder is 0, then we return min-max. If the remainder is non-zero, we will inc R11 by 1. The other thing we have to watch out for is that R11 doesn't go past R8. So if this divided by this gave me a result, but R11 was too big, yeah, then it could mean that this went past the bounds on the way. All right, this is some super small number, and when I do this divided by this, I get something outside of the upper bound if I don't do the test first. So I have to figure out if I'm going to increment R11. So modulo R8 then we just get R11 equals this. Now RAX is going to equal RD R9 modulo R8 is going to be a 1 if wait, there was another way to do this. I think there's like set Z. Is that what I need? Pretty sure there's an instruction that just does. Yep. Set byte on a condition. So if they are equal, then set RAX. So what does this take? It just takes a register, and then I have to test RDX, right? So I test RDX, which contains this, and then that right there happens, right? So if this is not 0, we get a 1 here, otherwise we get a 0 here. And then we do add, so this is going to be R11 plus equals RAX. Basically, if the remainder was non-zero, go up by 1, then do the test, and then, oh man, it's so annoying. You still have to do another comparison down here. Well, we can get rid of this. And then instead of doing the multiply, we're just going to do if this remainder is exactly equal to 0, then we're done. So we're going to do test RDX, RDX. And then if that is 0, we go to return, otherwise we jump to too big. I think that's the same. set NZ instruction. Let me see if I can get anything else. Yeah, it should just be one word register. Cannot be first operand. Do you just want something smaller? What was the name? Where do I have those register name tricks? AL. That do it? Okay, I don't love that because that suggests to me that it won't clear the upper bits. I definitely want to be able to use this to skip the multiply. So what I think I'll do is instead of trying to use the set instruction, because I'm not sure that I like where that's going, I could just clear it myself, right? I could clear it myself, set it, and then add that to R11. I could the other thing I don't love is that I have to test RDX twice, which seems silly. So why don't we try this? Why don't we try and look all the way up here at just branching in two different ways instead. If, come on, there we go. Oh, there we go. No. Okay, there we go. If the remainder equals 0, go to 2 small 0. Otherwise, we're going to go to 2 small 1, right? So we'll just test the RDX. Jump of 0 to 2 small 0. Otherwise, jump to 2 small 1. I think what we'll do is we'll put 2 small 1 here so we can actually just eliminate that. And 2 small is 1. And then 2 small 0 are the two cases. So, if we are in 2 small 0, then we had a remainder of 0. So what we do is we set R11 like so. We test R11 right here. If it fails, we return. And then finally, we jump straight to return min-max, right? Because we already know that it's going to be the right fit. That's the theory, right? And then otherwise, we do R11's got the divide, but we need to inc R11 by 1 because there's a remainder. Whoops. To inc R11 because it's got a remainder of non-zero. And then we want to test And there we go. So this looks pretty tidy. And so if R11 went too big, we jump out. Otherwise, we go to the too big case because we know that it's not a clean divide. Let me double check my logic here, but I'm pretty sure, yeah, if there's a remainder, then when R11 jumped up, this ink here will have taken it past, like before it went to the ink, it was too small. The ink will make it too big. That ink is implementing the ceiling here. Otherwise, we would be getting a floor. And we only ink when we need to because we're testing the RDX. But we were testing RDX for two purposes. To tell us whether or not we are in the case where we exactly hit an integer, and whether or not we need to apply the increment after we set R11 to RAX. And these are different here and here. So test, jump to here, move ink, compare, jump to here, jump to here. Okay. Does that still compile? Looks like it's still working. Alrighty. And then same idea here. We can do this better now. So here we always are setting R8 the same way. So that makes it a little simpler. So we can do the compare right away. And then instead of doing the multiply, we'll just take a look at the remainder now. The thing I have to do is figure out how the remainder actually needs to be tested. I don't know if testing with 0 is going to give me the right thing. So let me go and think about that part real quick. So here, if the remainder is 0, we're done, because that'll mean that R8 times R11 exactly equals R9. Otherwise, so when you get a remainder, right, I guess one way I could have thought about this is when you get a remainder, it means that R8 times R11 equals R9 plus the remainder, right? And then when you floor it or something, you're basically saying, let's like pretend there's no remainder or fractional part or whatever. And then if you check the remainder and it's 0, then you know that this multiply exactly equals the thing you want, which is what we're trying to find. So a remainder of 0 after the divide tells us to go to return min-max. Otherwise, we go to too small because we've gotten as big as we can on this side. So we can test RDX. If that's 0, we return min-max. Otherwise, we go to too small. There we go. Okay. So I think that is a pretty good implementation version for all of this. And now let's find out if we can finish this off for the problem we actually are trying to solve. So we got the building block here. We just need a quick Euler function here. I'm not sure why I put this above the prime sieve. That's weird. Okay. So here, we're just solving problem 4 of Euler, and that's all we need to know. So our answer is going to come back here, and here we go. Euler 4, proc, Euler 4, NP. Here the goal is to return the product. So what we want is we can set RCX to be our F, RDX to be our F, G, and R8 to be our H, right? Now I can actually make these a little bit tighter. doesn't like matter that much, but we know we can do it, and we should do it because we promised this thing that we would not pass at a target that was too big. So 998 would be too big because then we would be at 998,899. So 997 is the starting point. And we keep going until this says 1, 0, 0, and then we're done. So if this ever gets to 0, basically that's when we will stop. And then what we're going to do is, let's start by writing the loop body. So, or rather like the loop structure. So the loop begins if RCX equals 0, go to quit. So quit is going to live down here, where we're going to return RAX, or we're going to return. I'm going to put 0 into RAX preemptively, and then here we just do test RCX, and then if that's 0, we go to quit. Okay, now later we're going to want to do decrement counters. Counters. So I'm going to decrement. How do I want to do this? I want to say I'll decrement this, but if that was 0, then I want to set it to 9 and decrement this. And if that was 0, I wanted to set it to 9 and decrement this. So it'll be like this. If R8 equals 0, go to dec R8, otherwise it falls through. So that'll be like this. Test R8, R8, jump not 0, dec R8, dec R8, dec R8, jump to loop 0, right? So if it's not 0, we just dec and go to there. Otherwise, we go put an R8, put R8 back up to 9. And then we do if RDX does not equal 0, go to dec RDX, RDX, jump not 0, dec RDX, otherwise dec RDX, oops, otherwise put RDX back in the, up to 9, dec RDX, dec RDX, jump to loop 0, and then here we just dec, if we got this far, we just dec RAX, and then if RAX gets to 0, that will cause the break condition. So all of this is how we decrement counters and run the loop, right? We have a couple different ways to jump. Oh, this needs to jump to loop 0 still. Yeah. So if we find somebody's not a 0, we just do the simple decrement on that one. If they are a 0, we set them back up to 9 and then test the next digit, right? So if this is a 0, it becomes a 9, and the next one gets decremented. But if it's not a 0, it gets decremented and nothing else gets touched. So that should be right. Now, and if I test it, we should just be getting 0 here, dec r dx. We're getting an infinite loop. Okay. Let's figure out what went wrong there first. Okay. RCX is not 0, so can I just see RCX, RDX, R8? 7, 6, 5, 4, 3, 2, 1, 0. 8, 9, blah, 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 0. Da, 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 da. So are you telling me we never jumped to quit? How is that happening? Surely you must be in this loop still. 8. Test RDX. It's not 0. 7, 6, 3, 2, 1, 9, 7, 6, 5, 8, 2, 5, 4, 2, 2, 1. Must be something going wrong here. We go down to 0, and then we are going to decrement until this guy reaches 0, so we should get a normal decrement there. Then he's going to go, no, I'm not 0. He becomes a 9. No, I'm not 0. He becomes a 9. We dec RAX. Oh, I'm not supposed to dec RAX. So dec RCX. Okay, so loop exits. So there we go. We're checking all the 6-digit palindromes for nothing in particular and then returning 0. But now we can start running the actual test. So what we want to do now is let's see, R9 is available. So we're going to set R9 equal to the palindrome. This is going to take a little bit of work. So R9. First, we're going to move into R10, the integer 10001, 001, and then we're going to multiply that by f, RCX. Wait, I guess I'll do that on R9. Then using R10, I'll set 10010, so that's, we have this written down over here, right? 10010, 10010, multiply that by G, add that into R9, then we can move into R10, 1100, can multiply that by R8, which is H, add that into R9. And now I have R9 as the palindrome, which means if I can successfully determine whether or not, where is it? So I want to see if I can find bounded factors for this now, right? So, oh man, this is where things are gonna get weird. Okay. So I've been using RCX, RDX, and R8, but these are actually, like, these are all gonna be parameters. Find bounded factors. Yeah, I have, all of these need to be reserved for parametering when I do a function call. So what are some options that I have? I could immediately just switch all of this to using call-ly save registers. I think that might be the easiest thing to do. We just throw in some pushes and pops and use call-ly save registers so that we can call this guy who uses 4 parameters as well. Since he uses 4 parameters, we don't have a lot of caller save registers left over for us. So none of these. None of those are available. So we would only have 2 R10 and R11 are safe for us to use. So long as we don't carry anything over the call. So like here we can use R10 this way. But we can't do what we're doing, like as a temporary R10 is fine, but as something that gets carried over the call, we need to switch to, okay, yeah, this has nothing to do with anything. We're going to switch these up. So this is going to be, let's see, RDI, RCX becomes RDI, RDX becomes RSI, stack pointer R12. So R8 becomes R12. And then we need to include, let's see, where does our procedure begin here? We need to include some pushes here, RDI, RSI, R12. So we're just saying, hey, whatever was in those registers before, remember it, because we're gonna need to get that back later. And we're going to use those registers here now for these counters. Okay. So that makes things a little bit easier, but we're still not done because now we've got, well, first of all, let me do this part. All right. Now we've got a couple other problems. One thing is we need to figure out when do we do jump quit? Yeah. I'm going to rename this jump to fail. And fail is going to go mov 0 into rax right there. All right, now we want to figure out, actually, there we go. Now we want to figure out how are we going to do we got to do the function call here. So we need to move something into RCX that we don't actually have yet. We need to move into RDX, the min value, which is going to be 100, into R8, the max value, which is going to be 999, and into R9, we want to put the palindrome, which I've already done. And, well, funny enough, R9 contains our palindrome, and then here we call find bounded factors. push RDI, RSI, R12. So we need to do one more thing, which is we need to subtract from RSP 16 bytes. That'll be the space where we are actually returning the that'll be the space where we're actually returning the result. So we give it the stack pointer as the first parameter to use as its return pointer. It should then give us a situation where if the thing at RSP is, if RSP 0 does not equal 0, then yes, we actually want to do this a little more carefully. Let's save one more of these. R13. Got to do these in reverse order too, I forgot. R13. Okay, so we're going to use R13 instead of R9 here. Even though it was serendipitous for the call, we still need it to be there, and the ABI says we can't trust that R9 will still be what we set it as after the function call here. So R9 gets what's in R13, and now it can trample over the R9, and we still have the R13 for later. So if RSP 0 does not equal 0, we're going to go to success. Otherwise, it'll just go on to the decrements of the loop. So here we go. Test. Well, let's see. Let's move into, it doesn't really matter which one we grab. So we'll just grab RDX, the value at RSP, and then we'll do test RDX, jump if that is not 0 to success. So success is going to be like move into RAX the thing from R13, which is the palindrome. Not good. Oh, and we need to add in RSP 16, right? Here we took 16 off we increased here we allocated 16 bytes on the stack, there we need to deallocate 16 bytes on the stack. 90609. That's what it says our answer is. Let's see what the website thinks. Alrighty. That's another one done. Let's take a quick break here from talking to get set up on the next one. Sogarisu asks how many problems I am planning to do. And the answer is, well, there's a couple answers. So first of all, where is this? So here's all the problems. But Project Euler has a rule that they don't want you to publish solutions for anything outside of the first 100. So I'm never going to do more than these ones here. But I'm also trying to just do this, like right now I'm just shooting to do this for the month of March. So my goal is to do this every Tuesday and Thursday throughout all of March, and however many I get done, that might be where I stop. I am kind of enjoying it, so I might keep going or resume in a later month. But like I said, I won't do more than 100. I might skip some of them that I think are not relevant to the stuff I'm interested in practicing, and I might stop after the end of March, or not, or still stop later after a couple months of however long I'm enjoying it. But I'm at least going to do all of March, however many I can do. Okay, let's get into this one. So, it says 2,520 is the smallest number that can be divided by each of the numbers from 1 to 10 without any remainder. What is the smallest positive number that is evenly divisible by all of the numbers from 1 to 20? Okay, so I don't know how much of this I can explain simply, but this is basically a problem involving like fundamental stuff in number theory. Basically what we're saying is each of these numbers from 1 to 20, let me write it down. I think I know how I can write this down to make it clear. So let me zoom out here. Problem number 5. About there. Let's see here. Problem number 5. All right. Way zoomed in, so we can't really see the original title from this far zoomed in. That should be good. Okay, so that example they gave is what I'll explain first. So it says that 2,520 can be divided by all the numbers between 1 and 10 without any remainder. So one easy way to make a number that's like that is you could go like 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10, right? Now if you multiplied all those together and you said like that is x, well then x will be divisible by all of those things for free, right? Like you created x by multiplying them all in, so like x divided by 10 is whatever you get for that integer, x divided by 9 is whatever you get for that integer, and so on. They're clearly divisible. But x will be way larger than 2,520, right? I don't know what it is, but it's definitely bigger. So what you can do to make it smaller is you can break these down into their factorization. So this is like, 1 doesn't really factorize, it just is 1. But then, I'll just leave that with nothing written underneath it. So let's say here, I'm going to do factorize. And so this is like 2, this is 3, this is, I'll do it this way. 2, I'm going to put a little gap here. So our 2 factors will go on this line. Our 3 factors will go on this line. And then let's see, this is 2 squared. This is 5. Our 5 factors are going on this line. So I am using my ability to spot primes here to figure out when a new prime shows up. And then I'm figuring out how to write each number as a multiplication between primes, right? So it's factorized. Now, what I can do is say, okay, I need a number x that has the ability to be divided by 2 3 times, right? No matter how many times I multiply by 3, 5, or 7, x won't be able to be divided by 2 unless I put a multiple of 2 in there. It won't be able to be divided by 8 unless I put 3 multiples of 2 in there. But I don't need to have 2 times 2 squared times 2 times 2 cubed times 2 in there. So instead of x, which has 1, 2, 3, 4, 5, 6, 7, 8, this is like 2 to the 8. That's too much. And instead of like this, what is this? 3, 3, so this is 3 to the 4. This is 5 squared, and this is 7. Oops. This is 5 squared. Can't draw 2's today. 5 squared, and this is 7. This is way too much. So what I actually want is, if you look over here at like the number that they gave, 2520, what they're telling us is that there is a 2 cubed in there, there's a 3 squared in there, there's a 5 in there, and there's a 7 in there, right? So it's taking the maximum of each of these primes out of however many times they occur in all of these things, right? So how can we find that easily for the numbers from 1 to 20? Well, one thing I could do is I could go build a factorization table, and then for each number, I would grab their factorization. Their factorization would look like these things here. So each of these is a factorization, right? And I would get like, I'd put in a 6 and I'd get out the list 2, 3, and then I'd go, okay, 1, 2, and 1, 3. That's not a new max for either of these. 3 2s when I put in 8, that's a new max. So then when I'm done, I'd have a bunch of maxes, and then I'd just multiply that, right? But I would have to then build a factorization table, and then I'd have to use it in a way that's going to be fairly expensive. I think there's a simpler way, which is I could think about what happens if I combine these in one at a time. So let's look at what happens if I just grow this out one at a time from the number 1. So if I put in let's see. Basically what we're talking about is taking a least common multiple, right? So we have like n here, and we have the least common multiple of n factorial here, right? So let's see what we can do. If n is 1, that'll be a 1. If n is 2, I can make that a 2 now. If n is 3, then I'm looking at 2 times 3. I need to make that at least a 6 so that it's divisible by 2 and 3. If I put in a 4, well, now I need it to be divisible by 3 and 2, but also 4. And 2 and 4 have an overlap here, so I don't need to do 2 times 4, but I can need to do 3 times 4. So I can go to 12. 5. So I have a new prime now, so it's just going to be this times that. So 50, 60, right? So that's divisible by 4 and 5 and 3 all at the same time. Put in a 6. This is already divisible by 6, so no change. Put in a 7, and then you get 60 times 7. Let me plug that into a calculator to speed things up. That's 420. I guess this isn't least common multiple of n factorial. It's least common multiple of 1 dot 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 n. Okay. 7, let's see, 8. Is 420 divided by 8? Well, I've already got the ability to divide by 4, but I don't actually have the ability to divide by 8. But 420 can only be divided by 4. Once you do, there's no more multiples of 4. So I need to double it so that it'll also be divisible by 8. 9, again, there's only one multiple of 3 living in there, and we just got a new multiple of 3 that we've never seen before in 9. So I can put in extra 3, 840 times 3. That makes it 2520. And when I put in 10, this is already divisible by a 2 and a 5, so it doesn't need to change at all. So let's see. one way we could look at that, what just happened, is we could look at the pattern of like, okay, when did the number not change, and when it did change, how did it change? So it changed in these positions. And it didn't change here or here. So what's interesting about 6 and 10 is that they are the only ones that are multiples of multiple primes. And that's significant because that means that we can kind of spot the pattern here. Whenever we have something that's a power of 1 prime, so 4 is 2 squared, 8 is 2 cubed, so that's a 1 prime to a certain power. 9 is 3 squared, so that's a different prime, but it's still a prime to a power and no other primes. That's always going to be where the maximum of a particular prime increases, right? Before we see 3 squared anywhere else, we're going to see 3 squared by itself, because 3 squared times another prime is just going to be even bigger. So we always get a new factor thrown into the mix at the point of a prime or power of a prime. But then in order to use this idea, we're going to have to be able to detect that. We can check primes pretty easily. We could run the sieve system we have, and that would tell us if we're seeing a prime. And then we could maybe like square our primes until they exceed 20. And that would give us the list of all the prime powers. But then we would also need to know, like, okay, so whenever we see a 4, we'll multiply it by 2. So like, this is times 2 times 3 times 2 times 5 times 7 times 2 times 3. So if we built a table that gave us a prime power and the base of that power, and then gave us 1 whenever we saw something that was either the number 1 itself or not a power of a prime, then our answer is just the product along here, right? But I think we could do something even easier. That might be a useful direction to go, but I think we could do something even easier. So if you think about this, what happens when we combine 2 numbers this way? Like, let's take a look at the example like 4 and 6, because that's an interesting one. So suppose I just wanted to get the least common multiple of 4 and 6. If I just multiplied them, I would get 2 times 2 times 2 times 3, right? I'd get kind of like what I did here. I multiplied all of these together and I got all these extras that I didn't really need when I only needed this much. But what we could do, this wouldn't work for 2, 1, 2, 2, 2, 2. So 4, 6. Yeah, so if I have multiple numbers, it doesn't work. But if I have like lots of numbers, but if I have 2 numbers, if I have so if you say, I'll label this idea number 1, prime powers table. But for something that's only got to go up to 20, that feels like a lot of work. So I have another idea, which is, why don't we look at the idea of just multiplying 2 numbers? So idea number 2. Suppose A and B are 2 numbers. Then something we could do here is we could say, like, how can we easily compute the way to combine these so that we don't duplicate any of the prime factors that we don't need to. In other words, how do we compute the least common multiple of A, B, right? How do I write it this way? How can we compute this? And so the thing we could think about it as is like, each of these gets written out as some list of primes. So like A is P sub 1, I'll do it with powers like this, P sub 2 R2 dot 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 P sub m r p r to the r sub m, and b is, we'll switch to q, could be a different set of primes, q1 s1 q2 s2, right? It's its own prime factorization, qn sn. Might have a different number of primes, different prime bases, different prime powers, and the least common multiple of those two things is what happens when we multiply them together and then get rid of all the duplicates, right? So we kind of want to be able to say, like, if there are any things here that are the same, how can we, you know what, let's do this slightly differently. We could say that this is like, how do I want to do this? I'm not quite sure how to show this easily. This is more advanced thought than I know how to just demonstrate. This isn't going to be a rigorous proof here because I'm blanking on how you do the number theory work to show it. But suppose I have like a different prime factorization, s1, p2, s2, dot dot dot, p sub m, s sub m. So the ri is greater than or equal to 0, the s sub I is greater than or equal to 0, and the p sub I are distinct primes. Right? So the reason I'm saying that it's greater than or equal to 0 is some of these, like A might not use prime 1, but B does. So then it would put an R1 equal to 0, and then S1 would be not 0, right? And then when we multiply these together, we would get AB equals P1 R1 plus S1. P2 is R2 plus S2, dot dot dot. PM is Rm plus Sm. And what we want to do is we want to say this isn't quite right because the least common multiple of A and B is when you go P1 times the max of R1 S1, P2 times the max of R2 S2, dot dot dot, PM times the max of Rm Sm, right? Whichever one is bigger, we take it. So if they both happen to have the same power here, or the same base, we don't have to multiply them together. We just take whichever one has more. If they are both 1s, then we, taking the example of 4 and 6, for instance, from earlier, 4 and 6, we would want to be able to find the least common multiple, we need something that can be divided by 4, so it's got to have a 2 squared in it, but it doesn't have to have this 2 in it as well. So 2 squared, then it has to have a 3, because this has a 3 of 0, and this has a 3 of 1, right? There's like a invisible little 3 to the 0 here, wherever I left a gap. And over here, there's a little invisible 1 on that 3. So this is a maximum of 1 on the power of 3, and then we're done, right? So if that's what the least common multiple is, how can we compute that? Well, we can compute it pretty easily from this guy if we observe that the maximum value of R1 S1 is equal to R1 plus S1 minus the minimum value of R1 S1. Okay? So like this here, maybe it's not obvious why this is true immediately, but think about the max and the min is like selecting one of each of them, right? Max selects either R or S. Min selects, I'll switch this to I's. Min selects either R or S, but they select the opposite ones, kind of, unless they are equal, in which case they're each, it doesn't matter which one they're selecting, they have the same value. And then this here is the sum of both of them, so whichever one is the smaller one gets subtracted out here, and what's left over is the bigger one. Okay? So we can convert A times B into the least common multiple of A and B if we can find the min. Now here's the trick. The greatest common divisor, which we haven't actually talked about yet, but the greatest common divisor is exactly that. It's like P1 min R1 S1, P2 min R2 S2, da 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 PM min R M S M, right? So the greatest common divisor is the number that divides both A and B, and yet is not any smaller than it needs to be. So it's like it could, one of the divisors of A and B is always 1, but this here is as big as you can make the divisor and still actually have a divisor. So we can compute GCD, and then we can compute the LCM as AB divided by the GCD. Because when we do the divide, we'll get P1 to the R1 plus S1 minus min, P2 to the R2 plus S2 minus min, and so on, right? So the least common multiple of AB equals, or let me write it this way. So AB over GCD AB equals P1 R1 plus S1, P2 R2 plus S2, PM RM plus SM. Mad Flash in the chat, yes, I'm going to start writing some x64 in just a minute. I'm just working out some details of the problem first. Right, and then on the bottom we have P1 min R1 S1, P2 min R2, oops, that's 2, R2 S2 P sub M min RM SM, and then that is going to give us P1 R1 plus S1 minus min R1 S1. I'm going to skip over the 2 and just go to the end here. RM plus, right? Hopefully you guys have already seen where we're going with this, but I'm just going to spell it out. Right? And so like I said, each of these things now can be replaced using this rule, where R plus S minus the min of R and S is the max of R and S. And so we get that this is P1 max R1 S1 PM max RM SM, and that is the least common multiple of A and B. So then all we have to do, let me zoom out so I can finish the idea of this whole thing here. Then the least common multiple of AB equals AB over the GCD of AB. Now, if we have an ability to compute GCD, we're done, right? Because I said we can obviously compute A times B, and if I said if we can compute GCD and do the divide, we'll get the LCM. So how do we do GCD? Well, that's just going to be the Euclidean algorithm, right? The Euclidean algorithm gives us the greatest common divisor. So we're going to go write a Euclidean algorithm in a moment, but I just have to show how once we have that, we'll be able to solve our problem easily. So another way we could think about what's happening in this table is that at each point we have an accumulator, and we are accumulating that with the next thing by LCMing them together. So it's we're looking at 6 and 4 and going, okay, what's missing here? 2 is missing. So the LCM of 6 and 4 is going to be 12, because it's the 3 times the 2 times another 2 from the 4. And if we take the LCM of that and that, we'll get this. LCM of 12 and 5 will give us 60. The LCM of 60 and 6 will give us 60, and so on, right? So this will just turn into a 20, our final problem will just be to write a loop that for 20 steps computes the LCM of the previous, like the accumulator and the next value in our iterator, right? So let's go and try to write that. First of all, we need to recall the Euclidean algorithm. I suppose I will do another quick moment right here. Computing GCD of AB with the Euclidean algorithm. So this is a fun little number theory algorithm that I think is pretty common to like encounter in computer science education. So it might not be new to viewers who are interested in something like x64 programming, but just in case, I want to go over it. So the idea is we have two numbers come in. So it's going to be like I'll call this Euclidean of AB. And we're assuming something for my pseudocode here, we're going to assuming that 0 is less than A is less than B, okay? Then what we do is we say we want to use sort of the modulo operator, and we're going to say that our result, it's like this. If A equals 1, then we can return B. Okay? Sorry, that's not true. Yeah, sorry, that is not true. If A equals 0, we can return B. So we said A is less than 0, that's a mistake. A is less than or equal to 0. Now, otherwise, that will mean that A is some non-zero value and B is some even greater value. I guess this could also be equal, which is fine. Then what we do is we calculate a new value for B. I mean, the easy way to write this is as a recursive function like this, Euclidean. So you call Euclidean algorithm again, where your small number is then the big number moduloed by the small number, and your small number becomes your big number, right? But I want to write that as a loop. So that's the recursive way of writing it. So I want to give a procedural expression of it, just because that's going to match handwriting assembly a lot better. So the Euclidean algorithm on A and B is a loop where if A is equal to B, oops, don't zoom in. If A is equal to B, then we can return B. Or sorry, if A is equal to, I suppose that's true, but we're going to say if A is equal to 0, we can return B. We're going to create a quick temporary here. Wait, do I need to do that? B. Yeah, I need a temporary. So the temporary, way to think about it is A prime is the new A value is going to be B modulo A, and the new B is going to be A, and then we actually commit those into the values we've got, right? So that's the Euclidean algorithm as a loop. Now I could tidy this up real quick. So B prime is just moving A over. Hey, so yeah, this could be rewritten as temp equals B modulo A, B equals A equals temp. And you notice we can't immediately do A equals B modulo A because we still have to put that there, and we can't immediately do B equals A because then we throw away the actual value of A, so we need one temporary in the middle there. But that is how I'll do it. So we write a Euclidean algorithm, we wrap that in an LCM, and then we write the final loop. So time to do some of this. C linkage, G64, GCD, A, B, GCD proc, GCD end proc. So we're going to get RCX is our A value, RDX will be our B value. And now, before we were saying we would just assume that this was correct, but we'll include like the extra flexibility to like swap this and stuff. This could be a really useful function to use in a lot of ways, so having it just easy to call would be nice. So if A is less than B, go to skip swap, compare RCX with RDX, jump less than or equal to, skip swap, swap. So we'll put RDX into R8, then we'll put RCX into RDX, and then we'll finally put RCX or R8 into RCX. So there we've done a swap. Here's the skip swap. So now we can assume that A is less than or equal to B because we only ran this code here if it wasn't already. So here, if A was less than or equal to B, we skipped to here. Otherwise, we ran this thing, which swapped them, so now it will be true, right? I suppose we could just label this loop 0, because that's what's going to happen next, is we're going to need the label for loop 0. So we do the check. Test A. So this is going to be if A equals 0, go to return. So testing A, RCX, RCX. Hold on a second. Sorry, my phone was listening to me and thought I was talking to it, and it started talking back. All right, so where was I? If this is 0, we're going to return. Okay, that's not quite done. So if 0, then return. At the bottom here, we're going to have a return instruction, return label, and we're going to move into RAX whatever is currently in RDX, the B value, because we always return B. And then, let's see here. If we don't do the if, we do this this stuff here. So we need a temp. We already have a temp, so this is going to be Euclidean step. So I'm going to rename this GCD Euclidean. I like to include which algorithm the thing implements rather than just the concept that it of the function it computes. So there's like the GCD is the function it computes, but Euclidean is the algorithm it implements. So we're going to do R8. Right. So here we have to do, well, we got an issue. So we're going to have to first, okay, we do need a skip swap. We're going to transfer B into R8. Mov R8 into RDX. Now what's interesting is, okay, let's just do it up here, I suppose. Transfer B into R8, Mov R8 RDX. 8, skip swap. Okay, so R8 is the real register and RDX is the swap register. So we can skip this part because we know that these two will be equal by the time we reach here. Because the only way to reach here is to go here, 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 here. So here they become equal, nothing changes them here. Here they're still equal. So then R8 becomes the thing in here, A, and RCX gets the thing from RDX, which is like the temp that we've got from up here. So there's the swap. And then this goes to loop 0 still. If we don't need to do this, we jump straight to loop 0. Yeah, okay. Now, the reason we need to do that is because we have to do division work, right? When we do this guy, that is a divide. So now we have RAX needs to be whatever B is. So B is in R8. We need to clear RDX. And then we can divide all of that by whatever A is. What is A? RCX. Oh, this needs to be R8. Okay, so the divide tramples over RAX and RDX. So now RDX contains this thing, and that's good. So now B becomes A. So B is R8. So we move into R8 from RCX, and we move into RCX from RDX, because this already put the result into RDX for us. So then we pull that out of RDX and put it into RCX, where we are keeping the A value. Oh, yep, that's not a thing anymore. So we should now be able to get a GCD via the Euclidean algorithm. Let's try and get a GCD between 10 and 15. That said 10, which is wrong. So let's just step through it. I think that's the easiest way to find out why. They're in the right order. It's not 0 yet. So RAX becomes whatever's in R8. That's the 15. RDX gets cleared to 0. We divide by RCX. That's what's in A. So we have RAX divided by RCX, and then we get RDX equals 5, because that's the remainder. we move RCX. So RCX still contains 10. That goes into R8, which is our B. And the 5 goes into RCX. Okay. And, oh, well, there's the mistake. There needs to be a jump back to loop 0. There's our 5. Suppose I multiply this by another 2 and this by another 4. There we go. Suppose I take that to that, then I get there. All right, yeah, so that looks like it's giving me a good GCD. So now I can do a C linkage U64 LCM via the Euclidean algorithm. A, B. This is a pretty straightforward one. LCM, least common multiple by the Euclidean algorithm, is just going to be what we talked about on the whiteboard. I've got, let's see, RCX has A, RDX has B. I'm going to immediately call, wait, let me think. I'm going to modify RCX and RDX. So I'm going to move, yeah, we need, it's a little bit annoying, right? Because like what's going to happen here is this is going to trample all the values I've got. So I've got to save some. I got to save these. And I can either do that by putting memory on the stack that contains them and then reading them out, or I can switch to caller save registers that this won't trample, but then I have to put those on the stack and pull them out. One way or another, I have to switch to using memory here because I have a function that is calling another function. So there's never really a way, unless you don't need to preserve anything. I guess if I multiply them first, I only need to preserve one thing. So what I'm going to do is I'm going to push RSI, later we'll pop RSI and return. And then in the meantime, we are going to set RSI equal to A times B. So move into RSI from A, multiply into RSI from B, and then we still have C and D set up so that I can just pass those parameters right onto the GCD algorithm. So call GCD. Now RAX contains this. So what I want to do is I want to put I'm going to make RCX equals the GCD. And then I'm going to set RAX equal to RSI. RSI is the one that knows the A times B value. And I'm going to set RDX to 0. That way I can do this, right? I div that by R6. So R6 goes here. A times B goes here. RDX 0 goes in the high bits there. We do the divide, and now what do I get? Well, RAX now contains the result, and I return it. Okay, so give me the LCM of 2 and 3. 6 of 3 and 4. 12. Okay, give me the LCM of 6 and 4. Also 12. Give me the LCM of 12 and 5. 60. Give me the LCM of 60 and 6. Cool. Okay. So we're computing the LCM there. Let's finally solve the problem. Euler problem number 5. Proc and Euler 5 and P. So the goal here is to run a loop from one to 20, and at each step of the way, accumulate it and have an accumulator building it up. So I'm gonna need a stable counter and an accumulator. That's 2 registers. So I'm going to have 2 registers that are call or save that I can keep on this side over the function calls. And then I need RSI equals 1, RDI equals 1. So we've initialized them. We're going to label them real quick. So RSI is our counter, RDI is our accumulator, and then what we'll do is we'll have a loop here. The loop goes if the counter is greater than 20. And I can kind of say, like, why don't we put the counter at 2 initially? If the counter is greater than 20, go to done. Done will live down here. We'll set RAX to whatever in the accumulator. And this does test. Here's our counter. Oh, I have to, okay, we're gonna do compare our counter with 20. Jump if that is greater to done. Otherwise, what we do is we do accumulator equals the LCM of the accumulator and the counter, right? So I have to move into RCX from my counter, move into RDX from my, I guess I got that backwards, from my note. RCX gets the accumulator, RDX gets the counter. I call LCM Euclidean, and then I move into my accumulator the result, right? And then I go back and wait, then I increment. So I do inc my counter, and I jump back to the beginning of the loop where the test will run again and all that. Okay. So I need to actually call the new function. There it goes. Let's see if that's a good answer. Yep, hold on, let's do a sanity test first. We'll start with 10 here. Bloop. Okay, so that gave the right result. So when I put that in, bloop, it says that's the result. What did they say? All right, not bad. It's 5 problems. Oh, I like the look of this one. Oh, this is going to be a good one. Induction time? Yeah, I think we'll have to. Do we use? Actually, we won't need induction. No, not for this one. I'm gonna show you an even better way to do this. We already have. Yeah. This is gonna be great. It's probably if I knew some of these I know off the top of my head, like the triangle number one, but this one, I'm just gonna derive it. I don't really remember most of them. Triangle number formula is the only one I remember. So I'm going to show you my technique for deriving these kinds of things. All right. Alrighty. All right. We're going to start this one. So let me read it first. The sum of the squares of the first 10 natural numbers is 1 squared plus 2 squared plus equals 385. The square of the sum of the first 10 natural numbers, so you see they've inverted here, it's the square of the sum rather than the sum of the squares. The square of the sum is 1 plus 2 plus squared equals 55 squared, so adding those up first, then squaring, you get this much bigger thing, 3025. And then the difference between them is 2,640. So there's the gap between squaring first and squaring second is this amount. Find the difference between the sum of the squares of the first 100 natural numbers and the square of the sum. So we're doing the same thing, finding the absolute value of the difference between these two expressions for the first 100 natural numbers. Okay, so let me come over here. We're going to get on to problem number 6. not how you make a B. Problem number 6. So, alrighty. So, what we have here is we have like, I'm going to write down these as functions. So we have one of them is, let's see, 1 plus 2 plus dot 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 plus 10 squared. The other one is 1 squared plus 2 squared dot 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 plus 10 squared. When we take the difference between them, we get, well, they gave us the values here too. So 3025 minus 385, which equals 2640. Now, this wouldn't be too hard to just write, a loop for. We could just write a loop. It would go from 1 to 100. It would square each one, add them up into an accumulator, give us a result. Then we could do this one too, that's the same way, add them into an accumulator, then square it, take the difference, and we'd be done. But like I've said in other cases where I point out that there's like a simple brute computation way to do it, I kind of want to build up reusable things, and I want to like dig in to the math and to the programming so that we have stronger tools at our disposal for harder problems that might come up where that kind of approach won't hold, right? Where it just won't hold up anymore. So what I want to do is notice a few things here. So this side is the triangle number squared. So if you recall all the way back in problem number 1, the triangle number is that number you get when you do 1 plus 2 plus da 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 up to some n. So that's a triangle number. This over here is something different. So our goal is to figure out what that something new is, because we've already got a function for the triangle number, right? So if we can figure out how to compute this something new part, remember that's this for any n, then we'll be good. So let's focus on that, right? Okay. So here's how we're going to think about the new function. So the new function can be written down. First of all, I want to point out an observation, right? So the new function, like just the basic rule of the new function is that we're going to call it f for now as we're figuring out how to compute it, and then we'll use the bigger name for it when we type it into the computer, just so that it's got more organized, so that it's more organized and we can remember what it is and stuff. But for the math, we're going to use f. And then we're going to say f of n is, and then we could write it like this, 1 squared plus 2 squared plus dot 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 n squared. The more formal way to write that would be something like this. I equals 1 to n of I squared. And what we want to do is find a closed form way of computing that. And by closed form, what I mean is something that wouldn't involve a loop, basically. It's just so it multiplies and adds and things like that, subtracts and divides. So how can we do that? Well, I'm going to throw out a guess here. This is kind of looking like it's going to be a polynomial because we have something that's growing by a square each time. And if you if you ever look at things like, if you take the linear growth by 1, right? And then you go like, okay, well the gaps between these are 1s. And then if you take the growth of a quadratic, 1, 4, sorry, I'm blanking, 1, 4, 9, 16, 25, right? 36. So there's our quadratics. These grow by an unequal amount each time. So 3, 5, 7, 9, 11. But then if you look at this, those are growing by an even amount each time, right? So what's interesting here is like this is linear, or this is constant. This is linear. This is quadratic. And if we were looking at a cubic, we would see the same thing. There'd be sort of these tiers to how the growth looks. So whenever we're increasing by squares like that, 1, 4, 9, 16, 25, if these are the gaps between like some other value somewhere, so like, I guess I did that kind of the wrong way. Suppose I started off with excuse me, there we go. Suppose I started off with like 1, 5, 5 plus 9 is, what is this? It's not 15, it's 14, 30, right? So we're expecting that this right here is going to be cubic, since this is quadratic, right? That's what I'm expecting. So I think I'm going to just throw out the guess now. I wish I could make my eraser bigger. Is there a Milton expert who could tell me the hotkey that like makes your eraser bigger? Yeah. I don't know what it is. Ah, there we go. All right, so we're going to put out a guess. And our guess is that f can be written like a polynomial where we have degree of 3, right? We have a cubic, we're guessing that we can write this as a cubic polynomial or a degree 3 polynomial. Now we don't know anything else. We don't know if it has a cubic, quadratic term, a linear term, or a constant term. So we're going to just fill in that the guess like this. We don't know the values of a, b, c, or d, but we're guessing we can find numbers a, b, c, and d that'll be somewhat tidy and explain exactly this function, right? And that'll be a closed form way to compute it then, if we can find that. Now here's something else we know. We know that there's an easy rule that we can apply to this polynomial, which is that if you're trying to compute f of x, the way you do it is you compute f of x minus 1, and you add in x squared, right? That's sort of just an inference here, but like if I increase my n by 1 in this part, then what happens is whatever I already had stays there, and then the new value is that plus the square of the next thing. So if I'm trying to compute f of x, I take whatever you get when you go one less than that, f of x, and then you add in the x squared. So this was like in the domain of integers, and now I'm treating it like a polynomial where x can be anything. That might seem like it's complicating things, but it's going to mean we can use those strong tools of like simple polynomial algebra to come up with a formula. And since it's following the same rules that this is following, if it works, we should probably have a solution to this, right? It shouldn't be possible for a sort of real valued polynomial solution that matches the rule of this integer version to somehow give different results than the integer version on the integers, right? Hopefully that makes sense, but like we're kind of like solving the more dense version of the function, and then we're not actually going to use all of those points. We're just solving it that way so that we can use the very nice, easy, clean, real number mathematics that are familiar to us. Okay. So now what I'm going to do is I'm going to use these two things together. I'm going to combine those two ideas. So on one side, I'm going to have this. Well, I'm going to write this equation here, basically, but with this expanded inside of the f's. So first we have the left-hand side is f of x, and f of x is this. Ax cubed, at least according to my guess, I can write this for f of x plus cx plus d. And then I can write this again, but I have to replace all of the spots where x shows up here. I'm plugging in an x minus 1. So a x minus 1 cubed plus b x minus 1 squared plus c x minus 1 plus d. And then, of course, I'm not done. The right-hand side didn't just have f of x minus 1. So this part here has been duplicated here, or expanded out. But I still need to throw in that final x squared. Okay. So from there, what do I want to do? Well, I want to expand out these binomials here and here so that I can rearrange things into just plain terms of cubes, or x cubes, x squareds, x's, and constants. One thing I could do is I immediately see there's a d on each side, so I'm going to just say let's cancel those out for now because they shouldn't affect any of the other constants we're trying to solve. And then in the end, we can go back and solve for d later, right? Now what we have left is ax cubed plus bx squared. That's taking those d's out is just going to make this a little bit easier to fit on the screen, and it's a little bit less pen work and stuff. So now let's cube this out. So x cubed and we'll get an x squared. Okay, so we're going to get minus ax squared, right? So that's x times x minus 1, but there's 3 ways to do that, right? So let me spell this part out more carefully in case someone watching might not be familiar with how you expand out a cube, and so that I don't make a mistake too, really. So first we grab this combo right here. We go q, u, and u. That gives us an x cubed. All right. Then what we do is we go, how many ways can I grab an x squared, right? Because I can grab this, this, and this. But I could also do that by grabbing this, this, and this, or by grabbing this, this, and this, right? So then you get minus 3x squared. And then if you grab 1x, you're grabbing 2 negative ones at a time, so it becomes positive, but there are 3 ways to do that. 2 plus 3x, and then finally x minus 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 gives us a minus 1 at the end. So like that's how that will expand, okay? And now I'm going to do that in place here with the multiplication by a all the way through. So 3ax squared plus 3ax minus a. We'll do the same thing with b. So I'm going to bring it down here, plus bx squared minus 2bx plus b. So that minus 1 times minus 1 becomes a plus 1, and then times b, plus cx minus c. Okay. Very good. So now what I want to do is wherever I see like terms on both sides, we can just cancel those out. So these cancel. Bx squared shows up on both sides, so these cancel. Cx shows up on both sides, so these cancel. And so everything is canceled on this side. So all that's left on the left-hand side is 0. And what do we have left on the right-hand side? We have a negative 3ax squared plus 3ax minus a minus 2bx plus b minus c. Okay, now what I want to do is group things over here together in terms of the polynomial. Remember, this is a polynomial in x, right? So I have an x squared part, an x part, and a constant part here and here and here. And I want to reorder things so that those are sort of grouped together. Because right now it's grouped by the guess constants. A is grouped together, B is grouped together. So this is like a reslicing maneuver where I'm taking it and grouping it by a different principle. So 0 is going to become, so let's see, we only have one thing for x squared, so negative 3ax squared plus, all right, where are our x's? We have a plus 3a here. Oh, thank you, plus almost forgot these x squareds. Someone in the chat just reminded me. Okay, that would have led to having to track down the mistake later. Thank you, chat. Okay, so where are our x squareds? Negative 3a, and then we have a 1 over here, plus 1x squared. Okay, where are our x's? So we've handled that, we've handled that. Our x's are 3a minus 2b. We've handled that, and that's all of our x's. And then our constants. So we have negative a plus b minus c. Okay, so why is this helpful? Well, what's interesting here is we have a polynomial on this side in x, right? We have some polynomial in x which is equal to 0 on this side, which means each of these coefficients must be equal to 0. If this coefficient, for instance, was anything other than 0, then this is a polynomial on this side that is, you know, like, if suppose this was all 0, but then this part was like a 1, then this is on this right-hand side, the polynomial x squared, but that can't be equal to the polynomial 0. The polynomial 0 can only be equal to another polynomial if all of the coefficients are 0. So this gives us a new system of equations where we can say negative 3a plus 1 equals 0, 3a minus 2b equals 0, negative a plus b minus c equals 0. So now we can start solving for these things. A is going to be, let's see, we subtract the 1 over it. So a is going to be 1/3, right, to make this work. That means we're going to get, so that gave us this. These together will give us 1 minus 2b equals 0. That's going to give me that b is 1/2. And then if I combine all of those together into this one, I'm going to get negative 1/3 plus 1/2 minus c equals 0. So we're going to do multiply through by 6 here. So we get negative 2 positive 3 minus 6c equals 0. That's going to give me that c equals, that becomes a positive 1. So this becomes 1/6, right? Okay. So let's recall our guess. I'm going to transfer the guess down to here now. Well, actually, I'll transfer our a, b, and c up here. So a, I'm so zoomed out though. So a is 1/3. Here's what I'll do. I'm going to grab these guys. I'm going to transfer them over to here. A equals 1/3. B equals 1/2. C equals 1/6. So now we have f of x equals 1/3 of x cubed plus 1/2 of x squared plus 1/6 of x plus d. Now, we also know that when we put in 1, right, using our rule, let's just go and compute what happens when you put in the 1. So this guy here, when I put in f of 1, you get 1 squared and nothing else. So that'll be 1. So now we can use that to solve for d. F of 1 is going to be, well, let's see, that'll be just 1/3. This will be 1/2. This will be 1/6. And the reason for that is all of these x's here got replaced with a 1. So whether you square it or cube it or anything else, you just, the x disappears. And that's a d. And we also know that f of 1 is equal to 1. So f of 1 is simultaneously equal to both of these things, so we can put them side by side now. This right here is going to add up to 1, right? Because if you rewrite this as 2/6 and this is 3/6 and this is 1/6, you have 6/6 altogether. So that's just a 1. And then plus d equals 1. And so d equals 0. And so now all we have to do, we can finally, we found a function. We think it makes sense to say that 1/3 x cubed plus 1/2 x squared plus 1/6 x will give us our closed form. And let's just rearrange this a little bit. So I'm going to give them all a common denominator and factor out an x on the top. So step 1, we're looking at 2x cubed plus 3x squared plus 1x all over 6, right? So this became 2/6, this became 3/6, this became 1/6. Then we add them together. Now we can factor out an x, so we get x times 2x squared plus 3x plus 1 over 6. But is there anything we could do here? This is a bit trickier, but could we factorize this? This looks like it's going to factorize to me, right? So let me just do this over here. We're going to need a 2x and a 1 and an x and a 1. And if they're both positive, 1, 2x, 3x. Yep, this will work. Yeah. So there's our factorization. So we get the final thing is, let's write this from like increasing to decreasing order, because that's how I think these things like to be written usually. 2x plus 1 times x plus 1 times x all over 6. That's probably the way people standardly write this thing, because that's how they usually look. So what we have now is the closed form that is like nice and pretty to look at. We take our x value, we double it, add 1, take the original again and add 1, and then multiply them all together, and then divide by 6. So that should be the way to do it. Let's go type that in. So I'm going to start by coming up with a name for that. I'm done with Euler 5. Very good. So we have a triangle number up here. I'm going to group this with that. This is going to be the, let's see. So this is the square of the triangle number. This right here is the sum of squares. I'm going to call it that, sum of squares, U64n. We're going to pop all the way back to the top here and put this next to our triangle number function. So RCX gets our n, and our goal is to return n times 2n plus 1 times n plus 1 over 6. And there we go, proc n to p. So let's start computing this. So first of all, I'm going to move a copy of this into RDX. I'm going to shift left by 1 to get the multiply by 2. And then I'm going to inc RDX. I'm going to move into R8 n plus 1. So R8 gets another copy of RCX, and then we inc R8. And then we're going to multiply all of those together. So we're going to get RAX equals n times 2n plus 1 times n plus 1. You know, I really didn't stop and think about whether or not this is the fastest way to do it. If I do something more like this, for instance, I could square it Save the result, square it, save the result, cube it, so we multiply it by itself again. So that's 1, 2, 3, 4 multiplies. This down here is 1, 2. What? I did this wrong here. This should just be load effective address 1 plus RCX times 2. That can be done in one step. I could do that down here as well. Maybe I don't want to, but I think I do. 1 plus RCX. So there we go. We just get those like that. BYP, I don't know what Horner's method is. I'll have to look that up. Let me put it on my research list for over here. Horner's method. Ah. Get out of here. Value of 2x. Yeah, I usually like a Wikipedia page. Constant coefficients. The problem is to evaluate the polynomial at a specific value x0 of 0x. A new sequence of constants is defined recursively as follows: bn equals an, bn minus 1. Doesn't this just give you a super deep dependency chain? Or are you saying this is the way to do it if you don't care about the dependency chain? Because it doesn't look to me like this just like automatically finds something that's quick without caring about dependencies. It looks like it pessimizes the dependency chain. It does minimize moles and adds though, right? It's like you have literally, you do the multiply, you do an add, you do a multiply, you do one multiply and add for everything. If I were to do this, then I've got like 1, 2, 3, 4. So I got like extra multiplies for these, and then I still have the same number of adds. So I see. Horner's method, if you do it this way, the idea is to rewrite the p x0. Yeah, makes sense. So you take your highest constant, you multiply it by x, you add in the next constant, you multiply by x, and so on and so on. So you get a dependency chain that's deep, but you minimize multiplies and adds. This one here, that tells me how many there should be, right? So I should here have 1, 2, 3 multiplies and 3 adds, I think. Or 2 adds, something like that. And I'm kind of, let's see, that I'm going to get for free. 1, 2, I'm going to get 3 multiplies. I think this is going to be a good way to compute it. Because I'm getting the same multiplies and adds through the LEA instruction, so it's really compact in terms of layout coding. And then, although I still have to go and look at how, I need to go research microarchitecture stuff and see if this is a pessimization at that level, because I don't know. But the multiplies here are still in a chain. But it's only a chain of 3 steps instead of 5. Yeah, so let's do this way. Move into RAX from the RDX, multiply into RAX from the R8, multiply into RAX from the RCX. I'm doing this in like some crazy order here. There we go. That's what I said I wrote. That's what I said in the comments, so that's how I'm gonna write it. And then now I have to put into RAX all of this divided by 6. And there's just no easy way to do that as far as I know. You got to use a divide instruction. Maybe there's a good way to do this for constants that's better, but can I use a constant for the div? Hopefully. And then I should be able to return. No, I don't have an Euler 5. I have a sum of squares 10. No, you won't let me do it. Okay. Then in that case, I don't need anything else, so I'm going to move into the RCX, the 6, and then I'll divide by that much. Boom. 385 is the 10. 10, 10. Okay. So 385. Yep. Good. So now we'll just, did it say 100? Yeah, 100 minus. We'll just do this in C because it's honestly very uninteresting assembly code at this point. So we're taking the triangle number of 100 and triangle number squared minus the sum of squares should be our answer. Hey, hey, hey. All right, I'm going to take a quick notepad right here. Thanks for the note. I'm going to research that later to understand. Put this over here. All right. Okay. So we solved this one. Let's get the background noise going again. We could wrap it up in a minute. Here we go. So we've done 6. I'm gonna wrap it up and not do a code for 7. Wait a minute. I just read what it's called. Maybe we could do 7. Might just be able to knock this one out. So we have a tool that could do this, but there's a smart tool we might want to write that would go well with this problem that I might save for next time. We could like speed run it and be like, no, we've already written something that does the prime sieve. But the prime sieve, the way it works is you tell it what number to stop at. So I could say like stop at 1,000,000. This is telling us what index to go to. And so for that, what I really want to be able to do is take my sieve and extend it. So it's like you've got some list of primes and it went up to the first, you didn't know how far it would go, but you ended up getting 1,000 primes out or something. And then you want to say like, oh, okay, can I extend that to the first 10 million n? Like primes up to 10 million? Can you start with this list that I've already got and do an extended value up to here? And then it outputs another list of primes that start from where your first list started, and then you can join those lists yourself later. So yeah, I'm going to wrap it up here. I think this will be a great problem to start on next time. I'll take a minute to chat if anyone else has any questions or thoughts about what we did today or the project so far, but I think this will make a great problem for next time. Let's see, why don't we, I'm curious, why don't we peek ahead? Yeah, what else is coming up? So this is the kind I might skip. It's like, it involves a data table, which I suppose we could copy paste in, let's see, this is digits. So we could copy paste this into a text file and parse it with some C code. But, I don't know, maybe that would be interesting. Involves data processing problem. We could do this one. Let's see what else is coming up. Pythagorean triplets that sum to 1,000. Interesting. Sum of primes, that'll be pretty easy once we have our other prime stuff. More data table stuff. Again, we'll decide. That might be the kind of thing we skip. That might be interesting. Might be interesting to do some of those. The sequence of triangle numbers. So here we actually get them defining the triangle numbers. What is the value of the first triangle number to have over 500 divisors? Divisor counting. Then we will definitely want a factorization table. Interesting. Okay. Based on the pace, seems like we might get about 20 of these done. Ooh, interesting. Alrighty. Thanks, everyone. I will see you guys in 2 days.